All right, so before we get into calculating the formal charge of molecules, I think it's worthwhile to step back for 1 second and go through a topic that you may have covered in general chemistry, and that is just to cover what does it mean for an atom to have a charge. So understanding calculations leading to the charges on different atoms. This is something that it's worth spending a few minutes on before we dig deeper into the whole concept of formal charge for molecules. It's worthwhile just to sort of look at it from an atomic perspective. Okay, so let's look at the simplest atom we can possibly have, okay, and that is, for example, hydrogen. Okay, so hydrogen, so it's made up of a single proton in the middle here, and it has a single electron, okay, so electron. And of course, the electron has a negative charge. So we've got a positive charge. You can think of this as being the nucleus. Maybe we can just erase this plus charge here and just draw in the H, and just imagine that the H has got the plus charge around it. So we've got hydrogen, the plus charge, surrounded by a negatively charged electron. And hydrogen has, so one proton, one electron. These charges are equal and opposite. So they're going to balance themselves out completely. This atom of hydrogen has, with one proton and one electron, is going to be neutral. Okay, so of hydrogen is going to be neutral. So the charge, if you want, we can come up with a formula for determining the charge of an atom. Okay, and we could say the charge is going to be equal to the number of protons. Okay, so the number of protons subtract the number of electrons. All right, so if we have, for example, in this case, we've got one proton and we've got one electron, we're going to have a charge of 0. Okay, so this is a neutral molecule. Now imagine that we took hydrogen and we removed the electrons. So we're going to say ionized the hydrogen atom, so it's lost an electron. So in this case, we'd simply have a proton, or H+. In this case, if we had to do the calculation for this, we would have one proton, so that would be 1. Now the number of electrons here is now 0. So the charge of the hydrogen in this case would be 1. So 1 minus 0, so plus 1. Okay, plus 1. So this would be the hydrogen. It's sometimes called, this is H+, sometimes called the just proton. Now, if instead of having having no electrons whatsoever, imagine we had a hydrogen with, let's say, 2 electrons around it. So again, I'm just sort of roughly drawing things in here, but imagine we had, 2 electrons around our hydrogen. In this case, what would be the charge on our hydrogen? Well, we have still one proton, so that doesn't change. In fact, the nucleus is one of the things that, for our purposes, will not change very much unless you're dealing with radioactive processes. And we have 2 electrons. So now 1 minus 2 gives us a charge of minus 1. Minus 1. So 1 minus 2, minus 1. So if we've got 2 electrons around our proton, then we're going to have a charge of minus 1. So in other words, sometimes we write this as H minus. So you can write it as H minus. You can also write it as H. You can draw that pair of electrons in there, H minus. So the charge of the molecule is going to, or the atom, I should say. So used to saying molecules because I'm an organic chemist. The charge of the atom is going to be related to the number of protons and the number of electrons in a given atom. Okay, so let's just change a few things here. Let's, instead of having proton, let's have something like sodium, okay? And instead of dealing with hydrogen, yeah, so let's deal with sodium. So Na, or sodium, okay. And we can still use the same formula for sodium. If you think about the number of electrons around that are normally around sodium in its neutral state, we have sodium actually has 11 protons in its nucleus, and it actually has like 11 electrons floating around. And if we wanted to, we could apply this whole formula in this case. So 11 minus 11, which would give us a net charge of 0. But as you probably know by now, sodium actually has its first 10 electrons are all in filled valence shells. So the electrons in sodium, it goes 1s2, 2s2, 2p6. Okay, so that's 2, 4, 6, and actually it's the 3s1 that is the only empty and unfilled orbital in sodium. So all of these electrons in these orbitals, they're not going to change. So this is what we call sometimes a noble gas configuration, electron configuration. And this one of the 3s1 we say is the valence electron. So valence electron is the electron that actually can involve itself in chemical reactions because it's not part of a Nobel gas shell and not part of a full electron shell. So this is where the chemistry actually happens, is these transfers of electrons between electrons in their valence shells. Okay, so we can kind of just ignore the fact that sodium's got 11 electrons, and we can just focus on the single electron around it. And what we can do is we can change our formula a little bit. We can change our formula just to sort of, it'll end up giving us the same answer. If we say that we know, for example, that sodium has, in neutral sodium, has 1 electron in its valence shell. So number of electrons in the valence shell. Okay, and we're going to subtract the number of electrons. Okay, number of electrons in the valence shell for neutral atom. Okay, so the free and neutral atom, and we're going to subtract it. We're going to subtract the number of electrons in the valence shell for the given atom at hand. Okay. So this is always going to be, for sodium, this is always going to be 1. Now, if we're examining, let's say we're examining this atom of sodium, for example, we note that there is 1, we can change this answer is going to change here. So we can just adjust this by putting 1 electron in here. So 1 minus 1, so this would have a charge of 0 in this case. Okay, so 1 minus 1 would be 0. Now, again, if we lost this electron from our sodium, so if it became sodium without its electron, if we say ionized this sodium, then we'd be in a situation where we've lost an electron. It no longer has any electrons in its valence shell. So this number is going to change. In fact, it's going from 1 to 0. Now this number, the red one here, the number of electrons in the valence shell for a neutral atom is always going to be 1. That's never going to change. Okay, it's never going to change. But the number of electrons in the valence shell for the, it should append this at the end, it should say for the atom in question. This is going to be 1 minus 0, and so therefore the answer is going to be 1. So it's actually going to have a charge of plus 1, or just plus in general. Okay, just plus. Now, what if we had instead 2 electrons? Let's say we had a pair of electrons around our sodium. Each electron has a charge of minus 1. So you can draw a little minus charges for each of those electrons. Now, this is going to change our calculation again. We are going to have 1 minus, in this case, we've got 2 electrons in our valence shell. Okay, so 1 minus 2 is going to give you an answer of minus 1. Minus 1. So if we had sodium with 2 electrons, it would have a charge of minus 1. And of course, if we had a third electron, it'd be -2. If we had a fourth electron, it'd be -3, and so forth. Okay, so you start off with the number of electrons in the valence shell for the neutral atom, and then you're going to subtract the number of electrons in the valence shell for the atom at hand. Okay, let's do one last example. Okay, let's just change things a little bit. Let's do carbon. Okay, let's just do neutral carbon. And so neutral carbon. For neutral carbon, we'd have we'd have 4 electrons in the valence shell. Now, in this case, the atom at hand, so the one we're actually examining, has 4. So this number is potentially going to change. So 4 minus 4, so in this case it would be 0. But let's say we lost an electron. Let's say it lost 1 electron, and we only had 3 electrons around our carbon. This number would change. We'd go from having 4 electrons in the valence shell to 3. So the number of electrons in the valence shell for the neutral atom is always going to be 4 for carbon. It's always going to be 4. But in this case, this particular atom of carbon, we've lost an electron, and this charge here is going to be 1 or +1. So when it has 3 electrons around the carbon, it's going to be +1. And finally, let's say instead of, we go back to our neutral carbon, and if we were to add an electron, so an extra electron to our valence shell of carbon, we would have a total of 5 electrons. So then we'd have 4 minus 5, or -1. That would be our charge on the carbon. We'd charge with -1. Okay, so hopefully figuring out the charges on individual atoms isn't too challenging. Next, we're going to take the same concept and we're going to apply it to actual molecules.